Welcome to your premier destination for mastering concepts. Crack IIT, NEET, and all board exams with us.
In 1800, Sir William Herschel set up a simple experiment. He passed sunlight through a glass prism to cast a color spectrum onto a table, aiming to measure the specific temperatures of different colors of light using blackened thermometers. He placed a control thermometer just past the red edge of the spectrum, in an area completely devoid of visible light. Instead of reading room temperature, that control thermometer registered the fastest and highest temperature spike of the entire experiment. This temperature spike proved the existence of an invisible radiation that interacts directly with the thermal properties of matter. We call this band infrared. Using the Latin prefix infra, meaning below, the name denotes radiation that oscillates at frequencies immediately below those of visible red light. By examining the exact physical parameters of this unseen wave, we can deduce its unique physical behaviors, tracing why it acts as a heat wave and how it avoids atmospheric scattering. On the electromagnetic spectrum, compressing the visible light sliver exposes the gap just below red light and above microwaves. This infrared region stretches from 780 nanometers to 1 millimeter. Its inversely proportional frequency range spans 300 gigahertz to 400 terahertz, plotted below it. Despite these longer wavelengths and lower frequencies compared to visible light, infrared waves still propagate through a vacuum at the universal constant, 3 × 10⁸ meters per second. These precise physical parameters, specifically the extended wavelength, determine how infrared interacts with matter on an atomic scale. Every hot body in the universe emits infrared radiation. That includes the sun, a glowing iron rod, burning charcoal, and your own body. These emissions are generated by the rotational and vibrational transitions within excited atoms and molecules. So, what happens at the point of impact when an infrared wave strikes solid matter? The incoming wave transfers its energy into the target object's atomic structure. It forces the molecular bonds into motion, increasing the internal kinetic energy of the cluster. When you scale this localized kinetic energy increase across trillions of atoms, it manifests macroscopically as a measurable rise in temperature. This efficient transfer of kinetic energy is why infrared rays are classified as heat waves. But studying or directing these waves presents an immediate engineering problem. You cannot route infrared radiation using standard optical laboratory equipment. Ordinary glass absorbs infrared radiation. If you try to pass an IR beam through a standard glass lens, the glass itself will heat up, blocking the wave rather than transmitting it. To properly detect or disperse IR rays, researchers rely on specific crystalline prisms. As noted in this reference, they must use materials like quartz or rock salt. Rock salt remains transparent to infrared rays, allowing the waves to pass through without significant absorption. Understanding these atomic-level material constraints is a prerequisite for manipulating heat waves. This brings us to a macroscopic question. Why can infrared cameras capture distant objects through dense fog and atmospheric haze, while visible light is blocked? The answer lies in the mathematical rule governing atmospheric optics, Rayleigh's law of scattering. Rayleigh's formula dictates that scattering is inversely proportional to the fourth power of the wavelength. Input a short 400 nanometer blue wave, producing a high scattering value as it ricochets into a blur. Input an infrared wave greater than 780 nanometers, and the resulting scattering value drops. The physical consequence is that with significantly reduced scattering, infrared waves glide past air particles and water droplets without being deflected. This mathematical relationship between an elongated wavelength and reduced scattering explains why infrared boasts high penetration power through Earth's atmosphere. This table classifies the infrared region into 3 functional bands. Near-infrared ranges from 0.78 to 1.4 micrometers, behaving similarly to visible light. Mid-infrared spans 1.4 to 3.0 micrometers, utilized in thermal sensors. Finally, far-infrared covers 3.0 to 1,000 micrometers, emitted even by cold objects. Engineers select these specific bands depending on whether a system requires optical clarity for data transmission or specific thermal properties for heat detection. By exploiting minimal Rayleigh scattering in the near-infrared band, specialized cameras can capture detailed photographs of distant landscapes through dense atmospheric haze. In your living room, handheld wireless remotes use infrared light-emitting diodes to emit pulses at precisely 940 nanometers, carrying coded digital commands to appliances over short distances. The kinetic transfer properties of far infrared are deployed in medical thermotherapy. Infrared lamps penetrate skin tissue to relieve muscle pain and increase blood circulation through localized heating. In this thermal imaging photograph, we see how night vision operates. Sensors detect thermal radiation from a warm body, mapping those values into visual displays. On a planetary scale, roughly 50% of solar energy reaching Earth consists of infrared radiation. As seen in this historical photograph, humans have long harvested these waves directly for thermal power. Modern technology relies on translating the distinct physical behaviors of these IR subdivisions into practical tools. Because our eyes are blind to these wavelengths, measuring them requires physical detection hardware. Instruments like the thermopile or bolometer are built to measure small voltage changes caused directly by absorbed infrared energy. While ultraviolet radiation drives chemical reactions with minimal heating, infrared is defined by its capacity to transfer kinetic energy. The infrared spectrum illustrates how a simple mathematical shift in wavelength determines whether radiation is perceived as light or felt as heat.
Thank you for exploring the universe with us. Subscribe to Fundamental Physics for more.